Okay, welcome back to Structured Programming. Today we have a great guest. Oops, my mic is a bit
I
off.
think that might have been me. I turned mine on.
Oh, okay. So it is both a pleasure and honor for me to introduce Professor Anthony Hoskig, who is the director of the School of Computer Science within the College of Engineering and Computer Science here at the Australian National University. He is a member of the IEEE organization, a life member of the Association for Computing Machinery, and he was named a Distinguished Scientist of the ACM in 2012. Professor Hosking received his PhD in computer science from the University of Massachusetts at Amherst, and prior to joining the ANU, he served as a professor at the faculty of Purdue University, which is a very famous computer science university. He's an honorary professor at the University of Massachusetts at Amherst, and he has an extensive experience as a testifying expert in intellectual property litigation as well. Professor Hoskig's research interests lie in the area of programming language implementation and software systems, where he works on a huge number of different problems, arising, for example, from object persistence, object databases, distribution, managed language runtimes, language virtual machines, optimizing compilers, and many more, including memory management and garbage collection, which is the main topic of his lecture today. Up to you, Tom.
Okay, thank you, Giuseppe. Can you hear me now? Is that working? Yes, it is. Fabulous. All right, well, thank you. This is a great opportunity for me to stand in front of a classroom. It's been a few years since I've done that. As director of school, I tend to have other things on my plate. But one of the places I love to be is, in fact, in front of students like you, who are just getting into computer science and finding out about all the wonderful things and opportunities there are to work in this field. So I'm going to talk a little bit today about what has been a central part of my career, which is this issue of garbage collection. And I just want to point out that there is a book that I'm a co-author of, which happens to be probably the leading reference work on garbage collection and memory management available today. It's been translated into several languages. You can see versions of it here in Japanese and in Chinese as well. So this is you'd think, oh, this is a very esoteric topic. It's actually a very interesting and a very important topic, because every one of you has been programming over the last 2 semesters in programming languages that have at their heart this technique which is known as automatic memory management or garbage collection. Now, the reason it's an interesting problem is because it goes to the performance of the programs that you write. It's part of what's known as the runtime system. When your program executes, it's executing in an environment that includes not just the operating system and the hardware on which it's running, but also a support system for the programs that you're running, which include the garbage collector in those managed language runtimes, as we call them, such as Java and Haskell, as you've been using in Comp 1100, 1130. So I'm going to be telling you a little bit about this. I'm going to be starting out very simple and sort of motivating the problem, but then I'm going to dive into what is an interesting technical aspect of garbage collection and how to show that they are actually correct. Now you might say, well, does it really matter if they're correct? Well, of course it does, because if every one of you is writing a program that is underpinned by a garbage collector, then you want to make sure that it's not that any bug in the program is your fault and not the fault of the system on which you're running. So we need to provide robust runtime systems in programming languages that do the task, do it correctly and efficiently and unobtrusively. You as a programmer or you as the user of your programs as they're running should not experience interruptions in the behavior of those programs due to those runtime activities. So I'm going to start by starting very simple and motivating things. And I'll probably ask you a few questions as we go. But I'm going to start by visualizing some simple little Java programs. Now what you see here is a template Java program. It's got a main class, It's got a main method in that main class, and of course that's the entry point to the program. And then it's declared a node class, which has a field, the next field in that class. So what is that next field going to contain as the program executes? Well, it's a place for us to put a link to the next node in a chain of links. So this is the fundamental data structure for a linked list. And you may have encountered the linked list class in the Java libraries already in this course. And that's underpinned by an implementation that looks very much like this. Okay, so what can we do with this? Well, one of the things we can do in the Java language is to allocate objects. So I can write a program which will declare a variable. Let's call it A. And we can set that variable to be a reference to a new node object. And of course, we can run this program. And as we execute, you will see that we execute this main body of the method. And we invoke the new operation to create a new instance of the node class. And what does a node instance look like? It looks like this. It has a field that is the next field, and that's automatically initialized to be null, the null reference. Okay, so that's great. Allocation is interesting. The question is what happens next? Well, if you keep running this program, it will return, and somehow that node instance disappears. Now you might say, well, how does that node instance disappear? One suggestion might be that it's because we have exited the scope of that main method. That variable A is no longer accessible, and whatever A was referring to is also no longer accessible, and so can be deleted. It doesn't need to be there anymore. Obviously, this is more interesting if we start using this structure or using this node class to create more interesting data structures. So of course there is a next field there which I can use in that node object to allocate another node object. And of course we execute this, we get a node object. And then we move on, and we have now on return from that, we're going to set the variable A to refer to that node object. And then at this next instruction, we're going to create a new node object there, which is going to be initialized to null. And upon return from that new operation, we're going to come back here, and we're going to set the field of this node instance to refer to that new node object. And once again, if we were to exit, you would say, well, those objects are no longer alive, and you'd expect them to disappear. But something interesting happened here, of course, and it actually didn't show those objects disappearing, which seems to just suggest that there needs to be some mechanism to discover when objects become unreachable, no longer live. Well, one way to see it is if you, of course, do this. I can set the A variable to be null. And we can step through that to get ourselves a node object, have the A variable reference that node object, and the minute, of course, we set it to null, maybe then is the time that that object can be free. Of course, if I try to execute that next step, what am I going to get? What happens if I try to execute that next step? Yep. I'm going to get a null pointer exception because the A variable now contains the null reference. So if I was trying to do that, of course, I would get the error. Okay, so going back to this code, we're going to do this a little bit more. We're going to say, well, okay, if we can do that once, we can certainly do it twice, and we could set the next variable of the next variable. Oh, I can't type on this keyboard. To be a new node object. And if we were to run that, fix that typo there, and then off we go. Then what are we going to end up with? We're going to end up with a chain of node objects. There's A referring to that first one. We get another one which gets linked in. And then, of course, we get another one that's linked in. Now, if I was to say, I've got to edit the code. If I was to say that A is equal to null at that point, what would we expect to happen? What happens at that point? Processing my code. I think I've lost the connection. Let's try it again. What have I done here? That should have worked. We seem to be hung up on the website. Ah! Okay, so let me just get that example again. And I can't not type on your keyboard. Well, oh, we don't have a class node. That would be helpful. And yet again, we have a typo. Yeah. Okay, let's just execute this. We get a new node. We set the A variable to referring to that node. We then get another new node. We set the next variable of the object that's referred to by the A variable to refer to that new node. Now we're going to get another node. Come back here, and that new node is going to be assigned to the next field of that object. Now, what happened to the object that was there before? It was no longer reachable, it disappeared, right? Okay, so this system somehow is figuring out when objects that we allocate are no longer reachable. Here we allocated 3 nodes. At the end of this program, we only have 2 of them that are actually reachable from our program. Now, one way to approach this problem is to say, okay, I'm going to keep objects alive so long as there is at least 1 reference to them. And I could count the number of references that are available that refer to an object. And then when that number of references drops to 0, you might think, well, okay, that's fine for me now to free up that object. That's not a complete solution though, because we have issues that arise when it comes to what's known as cycles. So if I set that a.next here to be A, I run that program. I get an object, set the A variable to refer to it. I get another object, I set the next variable to refer to that. And then I set the next variable of that second object to refer back to the object that is referred to by A. Now, suppose at this point I set A to null. How many references are pointing at the node object? Currently I've got 2. right? I've got the reference from A to the node object, and I've got the back reference from itself to itself. So even if I set the A variable there to null, that object still is going to have a count in terms of number of references referring to it, which is greater than 0. And there's no way for me to tell that it's not reachable. Okay, so this demonstrates that an approach based on counting the number of references to an object to decide when it should be freed is not complete in the face of cycles. And we like to build data structures that have cycles in them. They can be quite useful. Okay, so what does a garbage collector have to do to be complete in capturing and finding all of the garbage? Well, it not only has to keep track of the references, but it has to follow those references. As the programming is executing, it's going to have to follow the references and to see which of the objects that have been allocated are still reachable. And you might say, well, okay, when does it do that? Well, the typical answer is it will do that when it runs out of memory and it needs more memory to be able to allocate new objects. And so garbage collectors have the job of making sure that there continues to be available memory in your programs that is not occupied by objects that are no longer reachable. If they're not reachable, then we can free them up so you've got the space to reuse for allocating new objects. Okay, so garbage collectors are part of the languages that you've been building programs in now for 2 semesters. Every single managed programming language today has a garbage collector in it, whether it's Python, whether it's Java, whether it's Haskell, whether it's Ruby, and so on. Of course, there are languages that don't have garbage collectors in them, such as C and C++, although you can put a garbage collector alongside a C and C++ program. But they don't typically come with garbage collection as a feature of the programming language. And there is this trade-off between the ease of managing memory automatically in this way, where you don't have to worry about when to free objects, versus programmers having the ability to say that an object is free. But of course, then the problem is that if I say an object is free too early and I've still got a reference to it and I try to use that reference, it's not there. And so that can create programmer errors. So garbage collection makes it easier for programmers to write programs without having to worry about when to deallocate objects and when to get into trouble because they've got a reference to an object that's no longer there. The system here is going to keep the objects around so long as there are references for you to use to access those objects. That's the fundamentals of garbage collection. And you might say, well, that's pretty easy. What's the big deal? Why is there a 600-page book written about this problem? Well, it's because it's much more interesting than that. The garbage collector typically wants to run when there's no space available so that it can give you space to satisfy further allocations in your program. Of course, if I allocate a whole bunch of stuff and then it comes time to figure out what stuff is still live and I have to sit there and wait for it, then that's going to create a big pause in the execution of my program, which your users might not like. I'm about to buy my tickets to the concert that's appearing on the lawns tomorrow, and I've got to get in there because they're in high demand and time is important. And suddenly I wait for a garbage collection while everyone else gets in and buys tickets. You don't want systems that are introducing those sorts of interruptions to user experience. So the big thing about garbage collection is how to make it unobtrusive to both the user experience and also how to make it efficient and also allow programs to continue to use the compute resources that they have to run ahead and do the work that they need to do, even while garbage collection might be going along in background. And that's particularly important because every one of your devices now, even your mobile phone, has more than one core on it. I don't want to stop all the cores on that phone just to do garbage collection. I'd like to keep some of those cores going, doing interesting things for you, and have garbage collection sit on another core doing garbage collection on the side with your programs as they're executing, so that the user experience is continuing to be a good one. All right. So I'm going to tell you today about the holy grail for garbage collection. What is it that we look for? And in particular, I'm going to be talking to you about some sort of guarantee that our collectors are correct. Not that they're just verifiable, but that they're verified. I would like to be able to make a proof about the garbage collector that you use in the system that's flying your plane, that garbage collector is not going to kick in while the plane's in the air and stall the plane in the air and make it crash. I would like to be able to prove that garbage collector has certain properties of safety that ensure that the systems that are built on top of it behave properly and behave correctly and provide the expected performance that you need. And I want to talk about garbage collectors that are what are known as on the fly. On the fly means that they execute at the same time as the application program is executing, so that they can sit on a different core, they can clean up behind you as you go. It's a bit like having a Roomba behind you cleaning up your room even as you're messing it up. Right? The garbage collector is that Roomba that's going to do the automatic cleanup even if you keep throwing your dirty laundry around the place. So I'm going to tell you a little bit about on-the-fly concurrent garbage collectors and how we can understand what they mean and how they run on modern machines. Okay, so there's a few terminology things that I'm going to use here. Every time we allocate an object there in those Java programs, what we're doing is we're allocating it into some part of memory, and that memory is what we call the heap. It's the dynamic allocation space for the program. Of course, your programs have memory which is statically allocated. It's allocated before the program even starts to run. It's allocated at the time that the program effectively boots up. There's space provided for it to execute in, and it will then execute in that space. But as the program executes, the heap is where we're going to add on to the memory allocated for the program. And that heap is just, it's an array of memory words. Your machine has a memory chip in it, and those memory chips consist of bits, and the bits are organized into words, and you can address the words using a pointer to addresses in memory. And that's exactly what those references that you saw in those Java programs as they run, those are actually pointers to locations in memory that have been allocated for use by the program. And those blocks of contiguous words may be discontiguous, so there might be spaces in between. And in fact, it's important that we make best of use of our memory so that we don't smear our rubbish all over the memory, but we try to keep it as compact as possible so that we don't leave big gaps that are unusable. And then the objects that we're talking about, the objects, I'm going to call them cells here. It's the contiguous group of words. Every object is a group of words that are contiguous, and those cells can be allocated or free, or they can be wasted, or even unusable. Ideally, we want things to be either allocated or free so that we can make use of them when we want to be able to use them. We'll often talk about programs as having roots. So when I ran that little Java example, there was a root variable there. That was the A variable that I called A, node A, and then that node A was assigned to point to a node in the heap. So that A variable is what we call a root. It's a root from the program that refers to the heap. So we have roots that have references that refer to objects. Objects have fields. You saw that every node object there had a next field, and that next field is what we used to store the reference to the next object in the heap. So we had a next field like this one, which had a reference to another node object. So an object is a cell that's been allocated by the program for the application. It's divided up into fields. A reference is either a pointer to a heap object or that special value null, the null reference, the thing that doesn't point to anything. And a field can either contain a reference. You might have fields that are things like integers or floats, other scalar values as they're called. But for our purposes here, we're going to mostly worry about fields that contain references. And those program roots are those local or global variables in the program that hold references into the heap. And the process of garbage collection or memory management using a tracing approach is to go from the roots, trace through all of the objects in the heap, figure out which ones are live, And the ones that we didn't find in that search are obviously dead. There's no reference that can reach them. So we talk about reachability. We call the program the mutator in this case because what the programs do, they mutate the objects in the heap. They allocate objects in the heap. They assign to references in objects in the heap, like the next field of an object, to refer to another object. So they mutate references in the heap. They change the shape of the object graph that is stored in the heap. And those changes can have the effect of disconnecting objects from the roots so that they're no longer reachable from the program. Those objects become unreachable. And the garbage collector's job is to execute its task to discover the unreachable objects and free them, allowing the storage that was previously allocated to those objects to be reused, recycled, and used for allocation of other new objects. So, this is pretty much a reprise of what I just showed you live with some Java code. But here I'm talking about a cell here which has some fields. One of the fields is a value, which is an integer, and the other field is a reference to another cell. Now, I'm using a language here which is a little bit different from Java in that it explicitly tells you which values are references and which values are integers, scalars. So in Java, of course, every object can only be accessed via a reference. Here I'm making it explicit that the object here that I'm talking about, this cell object, has two fields, a value and a reference field. And of course, this program starts out with a couple of variables A and B, which are the roots, and they're initialized to null. They don't refer to anything. They have a type, which is of reference to cell, that is initialized to null. So you can think of this program starts with those variables present in memory, part of the statically allocated space, if you like, for the program, but nothing has been allocated yet in the heap. When I allocate an object, I can allocate a new cell and I can assign it to be referred to by that variable A. That cell will have a value 0 for the value field and a value null for the next field. And I can do the same thing for another field which has a value 1 for the value field and a value null for the next field. But I can link those cells together by assigning the next field of that first cell object to refer to the object that is referred to by that allocation here to the B reference. And then I can even go and allocate another object, which is another cell, which has value 2 and also has a null reference in the slot. So if we step through this program, there's the allocation of that first object, there's the allocation of that second object, here's the setting of the reference in the object referred to by A, the next reference, to refer to the object B. And then the setting of the next field of the B object, the object referred to by B, to refer to a new object that has value 2 in it and has a null reference there in the next field. And of course, what happens if I say A is null? Some of those objects are now unreachable. So which objects are garbage here? Is it the one with the value 0, the one with the value 1, or the one with the value 2? Well, you can immediately see it. You look at this and you say, well, they've got a variable B that refers to the object that has value 1, which refers to the object that has value 2. So that object, those two objects are live, the one object and the two object, but the 0 object is dead. The garbage collector's job is to follow those references, and then everything that's alive will be kept, everything that's not alive will be dead. And so here is a garbage collector. Here's the code for a garbage collector. It has a loop that says, okay, I'll go through all of the roots. I'll figure out what they refer to. And then I will start following the objects that they refer to, and the objects that they refer to, and the objects that they refer to, until we get to a point where there are no objects left that I cannot find. Well, there may be objects left that I cannot find because they are garbage, and that's fine. And we're going to use a terminology here that is what's known as tricolor marking. So there's a very famous computer scientist named Edsger Dijkstra. I believe he may be on the list of people that were discussed as Turing Award winners in this course. Is that right? Yep. So Edsger Dijkstra is a Turing Award winner. That's the equivalent of the Nobel Prize in computer science. And he won a Nobel Prize as a theoretical computer scientist. He was particularly interested in problems of concurrency. And the hardest problem he ever faced was the problem of concurrent garbage collection. And in fact, the first paper he wrote on it, he got it wrong. And he had to issue a correction to that published paper because he was wrong about his understanding of whether or not that algorithm was correct. So we want to make sure that this algorithm is going to be correct. The model that he used for understanding garbage collection is to think about coloring objects as you reach them, or shading them if you like. We start out and say every object in the heap is considered to be white. We have not yet reached it. But as we encounter objects, we're going to shade the object grey. Now that object may have references to other objects, so until we have figured out those references, we're going to keep it grey, but once we've seen them all, we're going to mark it black. A black object is an object that we have encountered as we traced out. As we've traced out it's the references from that object, we've also made sure that all of the references from that object themselves are also reached. So there's this notion of objects being white, grey, and black. And the task of the garbage collector is to partition the heap into white and black objects, and as it works, it keeps track of where it is in that big sea of objects by keeping track of the grey ones as being the frontier of things it's seen so far. And when nothing is grey, it's done with its job. Either the objects are black, it's seen them, or the objects are white, it's never found them. Okay, so tricolour marking operates by starting out and considering all of the references in the heap, all of the references in the roots, and setting those objects to be grey. So if you think about this program, we've got a null reference here, we don't care about that. That root is got nothing to refer to. If it's not null, such as this B reference, then we're going to follow that reference and set the object that it refers to, the object if it's white, we're going to make it grey. And then we're going to enter a mark phase for that object. We're going to mark the objects that are reachable from that grey object. So now we're going to go and say, okay, while there's an object in that grey object, while there's a field in that grey object, it's a source field that we have not yet traversed, so we're going to go into a loop that considers all of the references that are held in that grey object. We're going to follow those references and mark the objects that they refer to. If they're white, we're going to mark them grey. And once we're finished with all of the fields in their first grey object, we're going to set that to black. Now you'll notice that there's a loop here. So we're going to go back to the top and we say, well, okay, while there's some source object that's black, that's grey, we need to think about it. Well, we have a source object here that's grey. It has a null reference, so there's nothing further to follow. So there's no need to set it to be grey. It's null. But we're going to set it to be black, that object to be black. And we're going to come back to the top of our loop. And there's nothing left that's grey, at which point we're done. There's no more roots to be scanned, there's no more grey objects to be dealt with, and we're done. We've exited this little program. Okay, so what's the collector done so far? It's traced all of the objects that it could reach from the roots. It hasn't touched any of the ones that it could not reach, and those objects are still white. The next step is to simply sweep through the heap. For every cell that exists in the heap, if it's white, then we free it. Otherwise, we set it back to white. So there we are, we have an object that's white, we free that object. Otherwise, if it's not white, we set it back to white. And we're done. So we freed up the garbage. Now we've got some space back, we can go ahead and allocate new cells, assuming that that was all the space we had to begin with. So we can allocate another cell, and we can continue to execute our program. All right, so that's a very simple little program, but we can make some arguments about its correctness. And when you talk about correctness in programs, you want to know two things. First of all, there's a safety property. The property for a garbage collector is that the collector should never reclaim live objects. That's a bug in the garbage collector. If I reclaim a live object, there's a chance that someone will come along because there's still a reference to it and try to use that object that no longer exists. And if it happens to be the object that is controlling my airplane and it's no longer there, I might be dead. Now, more feasibly, it's not so much that the collector never reclaims live objects, but that the collector never reclaims reachable objects. And that's an interesting distinction, and it comes down to the fact that the problem of discovering all the live objects in a program is what's known as an undecidable problem. It's a problem for which there is no algorithm that can compute the solution for all possible programs. So now we've suddenly hit an interesting part of computing, which is that there are some problems that you cannot write a program to solve them. Turns out that liveness is one of those undecidable problems. So we have to be a little more conservative. What we're going to say is that the correctness property here is that the collector never reclaims reachable objects because we know that those are the only live ones. It's okay for it perhaps to leave a little bit of garbage lying around. When you sweep your room, you still leave a little bit of dust in the corners maybe. Right? Okay, so that's the safety criteria for a collector. The liveness criteria is that the collector will eventually finish. You don't want it to spin there forever and never actually reclaim any space. You want to make sure that it makes progress. Because if it doesn't make progress, then your programs cannot make progress and they will stall, including the plane that they're flying. Okay. So when we look at a program like this, we can ask ourselves, what are the invariants that are going to preserve the safety property that we want for our program? At the end of each iteration of the mark loop here, there's a property here that there are no references from black to white objects. That's something that we can declare as an invariant in this program. If there are no references from black to white objects, then any reachable white object must be only reachable from a grey object. Because there are no references to black to white, the only other references to white objects can be from grey objects. And because those are grey objects, in this loop here where we're continually going until we have nothing left that's grey, eventually all reachable white objects will be marked. So those are invariants that we can write down against the lines of the code in the program here, and which we can then use to prove its correctness. And by prove, I mean in the strongest possible sense. We can write a mathematical proof that shows that those invariants are preserved, and those invariants are what ultimately gives us the correctness for our collector. All right, well, you'd think, oh, well, that's all very interesting, but you know, surely that was an obviously correct program. Where was it? Surely this program is obviously correct. I just made the arguments right there. That program is correct. I made the arguments based on those safety invariants. That at the end of each iteration of that mark loop, here's the mark loop, there are no references from black objects to white objects. So any reachable white object can only be reachable from a grey object, and I keep going while there are grey objects. And if I get to the end and then there are no grey objects, then there are actually no reachable white objects left. That's the argument. It's a very simple one. When it gets interesting is when we say, okay, how about the program changing the heap as we're trying to do this task? It's playing tricks on us. It's messing around with the heap behind our backs, concurrently, incrementally, so that we don't have to stop the program while we perform this algorithm, but we try to perform this algorithm in parallel with the program as it executes so that we can use that other core that sits on our phone. Okay, so the time it takes to execute your program is going to be proportional to the number of marked objects in your program. Right? The garbage collector How much work does it have to do? It has to mark all the reachable objects. How long does that take? Well, it takes as long as there are reachable objects. It's as many reachable objects as there are. How many objects does it have to mark? It has to go and do that work. And if I was to write this as a serial program, a sequential program, the users would notice those pauses. Those if I stop the program while I do this algorithm to find all the mark all the objects, the users are going to notice those pauses. There might be some, transaction in your ticket selling service for the concert that's on the lawns tomorrow, and that transaction might have a timeout because, we're not going to sit around waiting for someone to make up their mind whether they're going to buy the ticket. We'll put a timeout on it, and it'll close if we time out. Well, if I sit there garbage collecting, it's going to time out, and you're going to lose your opportunity to get the ticket. And if you've got real-time tasks like those that fly airplanes, then you might miss critical deadlines for those real-time tasks, like, what's the attitude of the plane, and do we need to correct its attitude to keep it flying? So one of the ways to reduce these pauses is to use what's known as incremental or concurrent collection, and you can even put it on a separate core in parallel. What you end up with in an incremental approach is to say, okay, I'm going to slice up the work of marking into little increments so that the pauses are not so long. We interleave with the mutator at appropriate points in the program. Could be a safe point in the program where you're about to allocate something, so you need to find a bit of space, you might be able to do a little bit of work. So that's one way, is to slice it up incrementally. Or if we've got multiple cores available, we run it in parallel, we can take those parallel exercises of the collector and do them incrementally interleaved with the parallel execution of the mutator, the application program. Or perhaps even better, we can do it in parallel, where we stop the program, we do a whole bunch of garbage collection work on different threads, and then we let the program continue, but we do that in increments. So that's a parallel model. Or what's known as concurrent, where we stop the program briefly just to check in, get a bit of information, and then let it proceed while we go ahead and do our work in garbage collection. That's a concurrent or parallel. Concurrently with the mutator is what we call it. So the mutator threads might pause just to synchronize a little bit, just to catch up with what the garbage collector's been doing or not doing. For the garbage collector, get a bit of information from the mutator program threads, and then let those run. Of course, you can variants of these, mostly concurrent, incremental, or even on the fly, which is just saying, okay, I'm going to pick times to do garbage collection. I might have to talk a little bit to the mutators to figure out the state of the world, but in this case, we're never going to stop the program. We're never going to stop the execution of the threads of the program, which might be running on multiple different parallel cores. Those threads might have to synchronize a little bit with the collector just to get the garbage collection process off and running, but then from then on, they run in parallel. Now, in this world, the pauses that the program experiences are very, very small, almost infinitesimal compared to if I put the collection happening while the mutator is stopped, while the program is stopped. But this is clearly an ideal. We'd like to be able to do this because we get the best visible throughput for our collectors, ideally, and we'd have low pauses, if any, in the programs. In fact, this can be made almost real time. All right, and there's variants, on the fly, incremental, all sorts of variations here. But the critical thing is that if we do this and we allow the collector to do work while the program is still running and changing the heap behind its back, we could run into trouble. So what can go wrong? Well, I mentioned that those gray objects represent sort of the state of the collector at any given point in time. And what it's trying to do is to move those gray objects through the heap until we get to no gray objects and all black or white. It's sort of a wavefront. It sort of washes through the heap objects, this coloring of gray and then ultimately black. It washes through, and eventually we're left with only reachable objects black and unreachable objects white. Now, it's okay if the program, the mutator program, changes things in front of that wavefront, because eventually we'll get there and see the change. But what's worse is if the mutator makes changes behind our back we've got our wavefront progressing through the heap, and then it changes something behind us. And that change could result in an object that we thought was reachable becoming unreachable and being freed even. So what it is that we're going to have to make sure that the mutator does not change a pointer behind our backs that makes a black object point to a white object, because there was that invariant that we had for our correctness argument that no white object refers to a black object. Okay, so this is subtle. It's not okay for the mutator to mess with things behind our wavefront. We know where we're up to. We don't want to change things behind us. But if it's going to do that, maybe we have a contract. It'll let us know. It'll tell us. It'll send us a message to say, oh, by the way, that object you thought, that thing you thought about that object is no longer true. It lets us know. It sends us a message. So this is what's known as the lost object problem. If the mutator stores a pointer to a white object into a black object behind our back, then we've got a violation of that invariant that no black object refers to a white object. That violates our correctness invariant. Especially, and this is key, what happens is if all the paths from any grey objects to that white object are destroyed, then the only thing keeping it alive is the reference from the white object, and we'll never see it. Here's how it works. Here's the example. How the mutator can hide an object from us. So let's suppose we've got these roots, we've gone through and we've marked that first object black, and we've shaded that second object grey from those roots. So we've processed the roots, we've seen the first object, we've seen the second object, we've shaded them appropriately. And the mutator comes along and does the following. It takes that reference and it stores it into the black object and then overwrites it with a null. At that point, we've violated our invariant. Now we've got a black object referring to a white object. And we'll never come back around and look at that black object and keep that white object alive. But it's worse than that. That's the error, in that we only have that black object, those objects live, and we'll never see that white object. Here's another error. And this is a more indirect one, but it's the same thing. We've got a black object that we've seen, a grey object that we've seen. The grey object has references to other objects, so we're going to have the mutator come along and change that reference there to point from the black object to the white object, and the grey reference gets dropped. That's a slightly different scenario. What we've done is we've hidden a white object that is reachable from a root via some black object, because we broke that link between the grey. That's what was keeping the object alive. We broke that link. Sorry, got to get back to my scenario 2. What's keeping that object alive is that link through that grey object. And we didn't drop the link to the white object, but we dropped the link that was keeping it alive from the grey object. We broke an indirect chain from a grey object. At that point, we're going to have again a lost object, because we've finished with all the grey objects, we've marked them all black. The collector now says that all those white objects are garbage, but this one obviously is still reachable. That's an error. All right, so there are these two scenarios that can cause problems, and what we need to do is to make sure that we prevent those scenarios from ever occurring. And what we do is we adopt a convention that the mutator is going to tell us if it does one of these changes. So the first approach is to use what's known as the strong tricolor invariant. That makes sure that there's no pointers from black objects to white objects. What we're going to do is have the mutator tell us that it's made a change that could cause a problem. So when we had that situation of the white reference there being stored into that black object, we're going to make the mutator recolor that black object to grey. Effectively, what we're doing is we're retreating the wavefront. We thought we were done with that first black object, but the mutator is now telling us, oh, no, you thought you were done. Go back and redo this one, because it's now grey. and then we'll go back and we'll find it, and we're all good, because that grey object will exist. Another approach is to what's known as keep track of deletions. Sorry, I've got to get through to this next one again, so that was fine. Did I miss something? Sorry. My animations, I haven't looked at these in a while. That's the indirect problem. This is the one where if we insert a reference into a black object that refers to a white object, then we have to make that black object grey. We have to retreat and make it grey. At that point, we're fine. That grey object will ultimately be processed, and the white object will be retained. Another approach is this one, which is to, instead of retreating the wavefront, to advance the wavefront. If we take that reference and store it into a black object, then we shade the target of that object grey to keep it alive. Even if we drop that reference, that's still a grey object, and we'll eventually see it, and we'll keep it alive. There are other ways of thinking about it, and the other way is to maintain what's known as this weak tricolour invariant. We prevent condition 1 and make sure that every white object that's pointed to a black object also has a grey object somewhere that it reaches from it to keep it alive. So it's got some protector out there, some defender, a guardian angel sitting in the heap somewhere that has got a bunch of references to that object, and so even if I have a white object pointed to by a black object, so long as there's a grey object that keeps it alive, then all is good. So the situation here is using what's known as a read barrier, which is to have if I have a grey object there pointing to a white object, and I delete that reference, then I shade the target on load to prevent us from having white roots, keeping it alive. Here's another approach. We can advance the wavefront when we delete a reference from a grey object to a white object. We can make that target object grey. And again, the guardian angel here is that grey object. Previously, the guardian angel was this one. But if we're going to delete that reference, then it has to transfer its guardianship to that second white object there. And the guardian now is keeping that other white object alive. So even if we happen to delete that reference, we still keep the white object. It's referred to from a black one. We're eventually going to find it. Oh, sorry, it's referred to from a grey one. It's eventually going to find it, even though there's a black reference, a reference from the black object to the white object. Okay. So those techniques are used in concurrent collectors, parallel concurrent collectors that operate on the fly along the side of your program to make sure that we preserve the safety of your program. And if we're going to reason about those sorts of collectors, we typically reason about it in terms of these invariants, these weak and strong tricolour invariants, and the operation of these things that the mutator, the program, is expected to do. If it changes the heap, it's going to inform the collector somehow by doing one of these operations to change the color of objects, so that then the collector can continue to work properly. Of course, the other issue is the question as to whether the mutator is going to terminate. Sorry, the collector is going to terminate. So, one property is safety, the other property is termination. How can we argue that that algorithm, that very simple algorithm that I wrote down in a single slide, ever finishes, that it actually gets done with its job, that it terminates, that the collector makes progress and the program is then able to make progress? So here's the argument. Eventually, all live objects are black. Marking an object only adds to the wavefront. That is when we shade it grey. Those mutator barriers, those things, that convention, that handshake that we had with the mutator, the program, to say, if you change the heap behind me, then you're going to let me know by doing one of those operations to change colors of objects so that everything is safe. Well, those mutator barriers only ever add to the wavefront. How do they add to the wavefront? By shading an object from white to gray and keeping, or even sometimes from gray to black, but keeping things up to date for the collector. If I'm allocating new objects while the garbage collector is still working, one thing I might want to do is to allocate them black so I don't add to the work of the garbage collector. So a new object that gets allocated while the garbage collector is in the process of figuring out what's live, well, if I just say it's automatically live because I've just allocated it, then that doesn't make any more work for the garbage collector. If I do that, it means that termination for the collector speeds up. There are ways of not doing that, but it tends to slow down the termination of the collector. So if I want termination, timely termination, typically I want to allocate objects black. And then we have this other barrier, this deletion barrier, the one that says when I delete a reference, I do something to the object that was deleted or the object from which it was deleted. So the deletion barrier avoids having to rescan or go back and deal with objects that have changed from, that have retreated from black to gray. That deletion barrier is one that actually keeps us advancing. It has some properties that allow us to have the program, even after the collector started its work at the snapshot event at the beginning of garbage collection, to continue to acquire white roots. It's allowed for the program to have references to white objects because the deletion barrier keeps track of reachability of white objects. If we don't have a deletion barrier, then we have to go back, and for termination, we have to go back and reconsider whether the collector has got any references to white objects, because those are new ones that it's found in the heap that were white, and we got them at the beginning. We got all of its roots at the beginning, but if it adds a white reference to its roots while we're working, we need to go back and check that it has no more white references. But the deletion barrier avoids the need for us to go back and check that the mutator, the program, doesn't have white references. But there's a little wrinkle here in that deletion barrier is not sufficient if we're allocating black. So just to give you a sense of that, here's a program. We allocate an object black. We take a reference and we put it into that black object. So I've taken that reference that just blinked right there, that one that blinked. I'm going to stick it into the black object. That's the program running. Now the deletion barrier would typically say, when I delete that reference, well, we're not deleting a reference from an object, we're deleting a reference from our roots, and we still have a problem. Okay? So it's not sufficient if we're going to be allocating black. It is sufficient when we allocate white. So if we don't allocate black, if we allocate white, then we only need that deletion barrier. But if we allocate black, we're also going to have that other insertion barrier. There were two kinds of barriers that I referred to preserve invariance, and that insertion barrier is still going to be needed. So allocating white, that's fine. We're going to go back and deal with those references at some point and find the objects. Same thing here. Allocating white or gray is fine. We're going to go back and find the objects. All right, so as I've mentioned, these on-the-fly collectors, they're currency. The way they trade on correctness is in this weak or strong tricolor invariants that are enforced by the convention that the program has to do things when it changes the heap. Those barriers, those deletion or insertion barriers. Now, at this point, you might be scratching your head, oh my God, this is so complex. And it's that complexity that makes us have to think very carefully about whether the algorithms that we write as garbage collectors are actually correct in and of themselves. Can we really believe these arguments that I've just made? I've just given you a whole bunch of different scenarios. Do they all add up to a proof that the collector program, that small fragment of code that I showed you, is in fact correct? Now, the interesting challenge is, can we do that for not just a simple little algorithm like I wrote on the screen, because that's a very trivial example of a garbage collector, but for a more efficient algorithm that is as used in your Java environments that you're programming with right now, or in your Haskell environments that you've been programming in 1100. can we prove the safety of a real production garbage collector, in particular for modern machines, modern computer hardware? And the reason I say this is because modern computer hardware is interestingly complex. It does not behave the way you might expect it to. The view that a given core in a parallel program, multi-core program running on your device, the view of memory that those different threads have can actually be different. One thread might see memory differently from the way another thread sees memory. The reason for that is because these processors have machinery built into them to speed up the execution of those threads, because going to memory is expensive. If I have to look at memory, it takes me 100 instructions to just even get to the memory to look at it. That's very, very slow. It's going to slow my programs down if every time I go to memory I have to take 100 instructions to look at the memory. So these processors have what are known as caches. Each core has a snapshot of the memory stored locally to it. And when it wants to access memory, it doesn't actually necessarily access memory, it just looks into the cache. And so long as that cache is what's known as coherent, then it assumes it's got the right view of memory. But managing the coherence of caches is tricky, and what's more, managing the notion of what's consistent in the cache is also tricky in the face of different cores making modifications to ultimately memory, because I can make a modification to memory that actually doesn't hit memory the minute I make it. It just makes a change in the cache. And that change may eventually get out to the real memory, but other cores are going to see the old values. And we have to worry about whether they've seen the right values. If I'm building a concurrent garbage collector like we've described here on modern machines, I have to be very, very careful about getting the synchronization right to be able to make sure that the view of memory that the collector has while the program is modifying it is actually correct and up to date with those modifications that the program is making. And I want to do that efficiently by using what are known as very lightweight synchronization methods on the machine, the core, the executable, the CPU of the machine has instructions to synchronize against memory operations. But I want to do those in a very lightweight way, using those lightweight synchronization instructions to enable my collector to be efficient. So this gets to be tricky. It gets to be tricky when we have to worry about whether the memory is up to date in what's actually in memory versus what the view of the memory is that the mutator program has. I've made a change, it's still sitting in a cache, it hasn't even hit memory yet. And I'm the collector sitting off the side trying to make sense of this mess. All right, so this is representative of some work that we did some time back. We built a garbage collector for Java, which is known as a real-time Java garbage collector. This was an implementation of the Java programming language that was designed to run on an unmanned aerial vehicle which had real-time properties, and where Java was being used to control the flight of this effectively airplane, an unmanned airplane, and making sure that that algorithm was correct and efficient, and keeping the thing flying was the challenge. So we built this garbage collector. It ran on a Boeing ScanEagle. It's a Boeing unmanned aerial vehicle, and we had to build properties into this collector that enabled it to be real time. It had to be real time because it was managing the flight of the plane, and we didn't want it to crash. It had to be able to respond to the sensors coming in. And we had these properties that we wanted. We had to have concurrent, on the fly, with wait-free constant time heap access. That meant that when the program, the thing keeping the plane flying, accesses objects in the heap, we didn't want to have to wait for a garbage collector. We also wanted to make sure that allocation was linear in the size of the object being allocated. And we wanted to preserve a property which is known as no fragmentation. Fragmentation occurs when I take a memory region, I allocate a bunch of things into it with gaps in between, and even though the sum of the free space is enough to allocate the next thing I want, because there's gaps in between, I can't get the contiguous space. That's called fragmentation. We don't want fragmentation. We want to have those gaps not exist. We want to be able to keep things compact. So we wanted a linear time allocator. That means it's the time taken to allocate something is in the size of the object. This means that when I write the programs, I can predict how much time that program is going to take to allocate objects, to access the heap, and so on. And of course, the challenge is doing this while also ensuring that the whole program doesn't slow down, that the throughput of the application is preserved to some degree. All right, so I can talk a little bit about this collector. It effectively captures many of the properties that we have so far. There's some information about how we encode things like the color. A gray object is one that's been marked. So we have a flag here that tells us whether an object has been marked. We have a way of threading together all of the live objects onto a work list. So when we encounter a live object, we put it on a list for the collector to use as the list of gray objects. And we have a length field that tells us something about those objects as we're working. And then we have this list, this work list of gray objects that the collector has to process, threaded through all of the objects it encounters. And each program thread, mutator thread, is going to have its own little local work list. So if a mutator thread does something to change the heap, it's going to keep track of that locally as opposed to having to wake up and tell the whole world about it. It's just going to keep track of it locally. And every now and again, it's going to check in with the rest of the world and provide the update. And then we have the accesses to the heap, and this is where we're going to put those barriers in place that we described earlier. So when you read from an object, you're going to be loading from some slot I, say, or when you write to an object, you're going to be writing a value into a slot I. And then we can allocate objects. And then there's going to be this protocol that every now and again, the collector and the mutator talk to each other just briefly to hand off information. Those mutators are going to hand off the changes that they've made in the heap, in that work list, and add them to the work list for the collector. And similarly, the collector is going to check in to make sure that there's nothing left. And this is just capturing the barriers that you saw recently, but this is now encoded in sort of a code language, showing you the implementation of that barrier. Those barriers capture the deletion and insertion barriers that you saw earlier in slides abstractly. When I'm writing to a field of an object with a value, I'm going to pick up the slot that was written to, the old value if you like, and I'm going to put that slot, that value into my work list. And I'm also going to mark the value that I'm storing. So here is the deletion barrier, and here is the insertion barrier. I'm inserting the new value, the new reference, into the slot of the object. Now, you might say, why am I showing you all of this code? Well, I'm just trying to make it clear to you that what we have here is a real low-level program that implements those abstract barriers, and this is pretty close to the code that we wrote. This is also pretty close to the code that we wrote for allocation, and it has a few things that happen. When I allocate some raw memory for an object O, I'm going to set the flag to a particular value. Remember I said the flag was about what the color of the object was, whether it was gray or black or white. I'm going to set the next field, because we're going to chain the objects that we need to work on into a list. I'm going to set the size of the object in terms of its length. And then I'm going to initialize each of the references. Typically that would be null. Right? Typically we're going to initialize the object with nulls, but maybe you initialize them all with something else. There might be other initialization values. And then this is the collector that we had, and it has a number of phases. There's a green phase, a blue phase, a brown phase, and a purple phase. And I'm not going to go into the details of those, but what you're seeing here is a breaking down of the collector into different parallel phases executing against the mutator threads. So this is our algorithm, and we're going to make arguments about the correctness of this algorithm based on the phases that we're in. If we're in the green phase, there are certain things that we expect, invariants that we need to preserve. If we're in the blue phase, there's another invariant we need to preserve. And we slice it up this way so that we can extract as much parallelism as we can from the collector operating alongside the program. Basically, we have an idle phase where there's no marking going on. The collector's not actually doing any work. But we transition into a phase where we start the process. And at this point, we're going to be expecting the mutators to do that marking work that we've put into their accesses to the heap. And then we have this storing and marking phase, this marking phase, which is going to do the iteration over the objects that are live to find the ones that we are going to mark ultimately black. And then there's a sweep phase at the very end that sweeps up the clean space. This code is very close to the actual C code that we wrote to implement this collector. So it's pretty much a boiling down to a little bit more detail of the abstract algorithm that I showed you earlier. And then there's, what happens in the marking phase. Okay, well, there's all of these adjustments to colors of flags and things to encode the coloring. And then there's this transfer of work from a mutator to a collector. So when we need to do the transfer, we're going to be transferring work from one working list to another working list, from one of the mutator work list to the collector work list, and there's a transfer operation that occurs. And then the collector is going to be dequeuing or pulling things off the front of that work list, and it'll keep iterating while there's things in the work list. That collector that I've showed you in that brief scenario there of slides is one that we ultimately wrote a mathematical proof against, pretty much against the code that you've just seen, where we verified the safety property that collector does not free up objects that are still reachable by the program. And the properties of that collector, again, were that it's real time, it operates alongside the program, it does not slow down the program never has to wait to allocate, the program never has to wait for garbage collection. It's effectively a wait-free garbage collection algorithm that the program itself has never interfered with except for occasional little check-ins. Now, there are some corner cases where, in fact, there can be delays, but those corner cases are very, very rare. There are sort of scenarios where you can stack up a whole bunch of things that have to happen, and then it's going to slow the throughput down to the point where it looks to be a delay to the actual program. But those occur very rarely, and we can put bounds on when those will occur. Particularly if we know what the allocation profile is for the application program, then we can actually prove bounds against this collector for the application program, if we know something about the way in which it's using memory. All right, so that's a very powerful story I've just told you, and it covers so many aspects of computer science. It covers issues of algorithm design, correctness, safety, termination. It covers issue of performance, building things that give you characteristics that you need for your application domain. It covers things of how do we reason about programs in a formal way that we can know that it's actually correct. And what I would like to impress upon you is that as you are studying this course and the other courses in our curriculum, you'll be touching upon elements of each one of these aspects of the problem. You'll have to understand the systems on which we're building. I mentioned the memory model of the architecture that you're running on. You have to understand that in order to make your programs correct. You will deal with issues of concurrency. One of the hardest known problems in computing is this issue of concurrency. Concurrency is widely studied, it's heavily studied, it's been studied for 50 years, and it continues to be a source of bugs in our programs, because at the end of the day, we want to make use of the hardware that's available to us, and the hardware we have now is multi-core. Everything is parallel, and we want to make sure that we can do things concurrently, safely, and with performance, and with user experience. So it even touches now on the user experience, this whole notion of what it is to interact with the machine as a human, the human-computer interaction here. If I have a garbage collector in an interactive environment that you're working with as you're working with the machine, and that garbage collector is continuously pausing things, that's not a very nice user experience. You want to provide smooth, predictable behaviors for the users and for the application. And that's where I will stop. How are we doing on time? Good.
Okay, let me...
I would be happy to answer any questions, if there are questions, if you're still awake. Because by this point, you're probably sick of references moving around on screen. If this is something that interests you, and I will say that there's so many problems in this space that are interesting, please come to talk to me. This is an area of active research, not just by myself, but others in the school. And we will be happy to try and find you a little project that would have something to do with this space of things, interacting with the programming languages, the hardware, the runtime systems, and how they actually come together to make the platform on which you write all your programs, all those wonderful programs that you're writing in this course. They want to get out into the nice sunshine. I don't blame you. Are there any questions online?
Yes. We have Java versions up to Java 8 have introduced multiple new Java classes like ZapDC and Shonagar. Hopefully I'm pronouncing it right.
Yep.
Are they promoting enough to become the new default in the G1DC in future?
Okay, so every one of those collectors has different properties. Some of them are optimized for throughput. Okay, some of them are optimized for pause times. Some of them are optimized for large heaps versus small heaps. Some of them are optimized to work in constrained space versus lots of, they can be a bit sloppy about how much space they need to operate. So every one of those garbage collectors has different behaviors. And a lot of the time what happens is you're looking at your application, you're asking the question, does this garbage collector fit my needs? And running with the garbage collector that appears to fit your needs. If you're interested in throughput, you do not want concurrency getting in your way. It's lots of little interruptions. If you want throughput, just be prepared to stop, let the garbage collector get in and do its job in parallel as fast as it possibly can, and then you get back to work and you blast ahead as fast as possible. If you want small pauses, you might have to put up with the fact that the collector is going to be prodding you every now and again just to say, I need something from you, I need something from you, and that's going to give you a little bit of jitter in your behavior, in your performance. One of my colleagues here is probably, I'm happy to say, he's actually the leading implementer of garbage collectors in the world. He's currently on leave from the ANU at Google, where he is working on the garbage collectors that sit inside the V8 JavaScript engine that's inside the Chrome browser. And he is actively working right now to improve your experience and the experience of Google in their data centers when they're running these Java programs and these JavaScript programs in browsers. There is some recent work in the field that I can point you at that actually suggests that some of these older collectors that are in Java now, so someone said, recently, Java has added these collectors. Well, actually, those collectors have been in development for 10 to 15, maybe even 20 years. G1 started about 20 years ago. It took that long for it to come into production. And those collectors now are even starting to show their age in terms of the desirable properties that we want from collectors these days. So it's an evolving field. There are new collectors being designed. There's some work that my colleague Steve Blackburn has done recently that is demonstrating that you can actually have your cake and eat it too. You can have properties of collectors that are desirable and still get performance that is also very, very good. And in fact, an improvement on those existing collectors. Now, that's a prototype, but there's some work being done to bring that prototype into production. And so that's a very exciting thing because it improves your experience, it improves Google's experience. It saves money on their power bills in their data centers because they can make efficient collectors that run effectively and use less power effectively in their data centers. So horses for courses is what I'd say, but there is some evidence that we're getting to a point where we're starting to see even better improvements on the collectors that are currently in Java as it's currently delivered to you. But again, choosing a collector is about understanding your application domain. You don't want a real-time collector like I described if you're not flying an airplane. You might want something different. You're not quite as interested in the very, very predictable properties. Any other questions?
Another follow-up question on this. Was it essential that you told G1DC because you plan out faster than legacy clusters, or was it due to improvements in hardware design and changes in every program code? Would you say do the older clusters do maximum own hardware or own software?
So there are some hardware issues that arise in the choice of collector, but the primary thing that G1 brought was the ability to deal with larger heaps, because G1 is what's known as a region-based collector. It takes a very large heap and it splits it up into regions, and then it manages those regions somewhat separately so that you don't have to spend all of your effort on a great big memory space. You can just focus on the parts of the memory where there is work to be done in obtaining free space. So you don't need to collect memory that is densely packed with live objects. You can break the space up and focus on the regions that have the most likelihood of most benefit from garbage collection. Any other questions? If not, then I can go off and write. Oh, yes, there's a question. So does the collector use memory itself? Yes, it carries some payload, of course. Ideally, you want to minimize that. So some of the techniques that we used there and the way that we threaded the data structure for what's live into this, we took all the objects that we wanted to process and put them on a list. That's effectively minimizing any data structure that has to keep track of the gray objects, say. We don't need a separate data structure around it. It's just threaded through the objects. And that minimizes our memory footprint and gives it predictability. Yeah. So yes, you have to worry a little bit about the collector itself. You know, some collectors will actually have objects that they create and use along the way that they ultimately collect also. So they may create garbage of their own if they're working. Any other questions? All right, well, that means Friday is actually my research day. I tend to focus on my research on Fridays. My Fridays right now I've spent working on the new edition of that book that I showed you on screen earlier. We are almost to the point where we're ready to send it out to reviewers to pick it apart on the changes that we've made to the book, but we've actually got a new version, new edition of the book coming out. And I'll be working on a section of the section I'm working on right now is the section on continuously compacting concurrent collector, the C4 collector, which is very similar to the Shenandoah collector, which is the one that's in Java right now. So I'm writing up that section of the book at the moment. Okay.
Fantastic. Please join me in thanking our guest for being here.
And enjoy the rest of your long weekend. Get some relaxation time in. Okay.
We're done. Let me stop the recording.